my name is Gianluca Bontempi. You are welcome to the presentation of my paper on learning causal dependencies in large-variate time series. So the motivation of this paper is to use causal inference in order to infer possible causal dependencies in large-variate time series. So large-variate time series is a very challenging setting for causal inference, because we could have a very large number of features and there could be dependencies between features which are on the time dimension, on the space dimension, for instance in the case of spatio-temporal time series. And it's extremely possible that, given the large intricate nature of dependencies, almost any time series is correlated with the other. And the goal of causal inference here is indeed to discriminate between dependencies which are purely associative and effective causal relationships. The conclusion of this paper will be to make an extension of the D2C approach, which has been an approach published on JMLR some years ago, which was based on the idea of using supervised learning in order to extract useful information from observational data and return the probability of the existence of a causal dependencies between a pair of variables. In this paper, we will propose an extension of the D2C approach, which will be called context-aware D2C, and a justification of this new approach will be done in detail in the paper. I won't have time to do this today, given the short time of this presentation. And the third contribution of the paper will be the assessment of this algorithm on a large number of large-variate synthetic stationary time series. So the starting point is the dependency to causality approach. And the idea of this approach is that if you have a large amount of observed variables, and you select a pair of these two variables, it's possible by measuring a certain number of statistical descriptors to implement a classifier which is able to return the probability of the existence of a causal dependencies between these two variables. So the idea that we could see causal inference as a sort of supervised learning tasks, where the inputs of these supervised learning tasks are features describing the probabilistic dependency, and the output is a class which denotes the existence of the causal link. So this D2C approach is made of two steps, a training phase and a prediction phase. In the training phase, we generate and simulate a large number of Bayesian networks, of DAG, of directed acyclic graph, for which we know everything. We know the structure, we know the functional dependencies, and then we could simulate a large data set. Now, on the basis of this observed data set, we could extract for each pair of variables a certain number of descriptors, which in the original paper have been shown to be asymmetrics, and so contain one of the major properties of causal dependencies, which is indeed asymmetry. And so for each pair of nodes in the DAG, we could measure a certain number of descriptors, make a vector, and associate them to the existence of a causal relationship. For instance, here for the pair 1, 2, we could extract a certain number of descriptors and associate 1 to mean that 1 is indeed a parent of 2. Concerning the pair 1, 3, 1 is not a parent of 3, we'll put 0, and we could as well collect a vector of descriptors. And since this is done in simulation, we could imagine to generate a huge amount of Bayesian networks, a large amount of data set, and then train our classifiers with a large amount of samples. Once this classifier, which in the original paper was a random forest, has been trained, we could imagine to use that for a prediction phase. Suppose that we have a data set, we have two variables of interest. We could estimate on the basis of the data set the Markov blankets of the two variables of interest, and for these two variables of interest compute a certain number of descriptors. Once we have these asymmetric descriptors, we can plug into the classifier that we have trained beforehand and then return the classified prediction. In the original paper, we have shown that this approach is competitive with state-of-the-art techniques of causal inference. In this paper, we make two main contributions. One is to change a little bit the nature of the algorithm. So in the original approach of D2C, we need to identify first the Markov blankets of the two variables of interest, and we need to define within these Markov blankets which variables are potential causes and which variables are potential effects. In this perspective, you could imagine that we have a sort of bootstrapping procedures, but which at the same time induce a vicious circle, because in order to learn the causal relationship between two variables, two candidates xi and zj, we should already be able to infer their causes. The idea of the context-aware D2C is to remove the need of this bootstrapping phase. And so the idea is to remove the need of a preliminary causal feature selection step by adding indeed a descriptor which is able to take into account the nature of the terms of the Markov blanket. And this descriptor is based on the interaction. The interaction term is a trivariate term estimated on the basis of mutual information and conditional mutual information, which in previous work we had shown to be useful in distinguishing between causal patterns. So this is the algorithm that we conceived, that is called context-aware D2C. The idea is not to have any more a causal feature selection step at the beginning, but to start with a very simple univariate ranking algorithm. So the idea is that we rank the most relevant variables for Zi and Zj into the sets Mi and J, and for each pairs of these two sets we compute a set of asymmetric mutual information descriptors, like the ones computed in D2C. But what is different than now, for each pair Mi K and MJK that belongs to the Markov blanket Mi MJ, we compute as well the context-aware interaction information descriptor. And then the algorithm proceeds as the original one by training a classifier using it for the final prediction. We have been shown that in the paper that by introducing this additional PI descriptor, we can get rid of the preliminary causal feature selection step, and by simply using a ranking, we can as well obtain good performance in terms of inference of causal dependencies. And this in particular for a very difficult case, which is the case of multivariate time series inference. And so in order to assess the quality of this algorithm, we have been performing causal inference experiments on a large number of simulated stationary time series characterized by nonlinearity, large dimensional and cross-sectional dependencies. Since the goal was to assess the quality of the algorithm in inferring causal dependencies, we started from synthetic data for which we are aware and in possession of the correct and underlying causal dependencies between variables. And we have been benchmarking the proposed algorithm CAD2C against the original D2C and several state-of-the-art causal inference algorithms like ItonPC, like IAMB, like Gauss-String PC, and the more conventional Granger test. The results are contained in the paper and shown here in terms of balanced error rate. We made two sets of experiments, one for a small number of nodes, so for a small number of random variables, smaller than 100, 1 second experimental setting for a number of nodes bigger than 100. And from the distribution of the balanced error rate accuracy for the two cases, we can see that this technique we propose is both competitive and outperforming the original D2C, and both competitive and outperforming a lot of state-of-the-art algorithms. So I invite you to take a look at the paper and to contact me if you have any sort of questions, and if you are interested in using and testing this algorithm, to see and to take a look at the R package D2C, which is available on my GitHub, and do not hesitate to contact me if you have any sort of question. Thank you for your attention and have a nice day.